Okay, let's have a look at this question from integration part. Before we get started, I really want to say that this question is actually very tricky, very hard. But most important thing is, it's not every question is like this kind of difficult. And I just want to tell you and show you how a complex question like this can be broken down into various parts using the ideas we have achieved or learned and eventually approach some very difficult task. Okay. I definitely do not want to scare you off with this horrible question. It's not actually horrible, it's actually quite interesting. And because it's quite interesting, so I want to show you, okay? Now, let's have a look at the question. A sketch of the graph y is e minus x sine x for x greater than or equal to 0 is shown below. The areas of the finite region spanned by the curve and x-axis are denoted by a1, a2, an on all the way to infinity. First part, find the exact value of the area A1. Okay, finding the area of a graph. That means, and you can tell from the title, it's about integration. So when we're integrating, we need a function, and I think it's pretty straightforward that the function must be e minus x sine x. Integrating with respect to x. And what about the bounds then? The lower bound you can read off from the graph, it should be 0, but the upper bound is a no at this point. So how shall we determine the upper bound? Is our next goal. So look at the graph now. Look at the function e minus x sine x. We know that e minus x is always positive for x in real. So whenever it reaches 0, that means it must be sine x equivalent to 0. Okay? And I think you can tell from the graph sine x equal to 0 when it's 0, pi, 2 pi, 3 pi, and it goes on and on. And a1 is the first area in the graph. So I think it's very straightforward to tell that this is actually pi, 2 pi, 3 pi, 4 pi, and it goes on. So we are actually integrating between 0 and pi. Okay, now we have such a function. The next thing is integrate this function. How shall we get started then? Well, you can see it's a product of functions, right? It's a product of functions. So I think it will be most easy to use integration by parts. Let u equivalent to sine x, then du dx is cos x. And let dv dx be e minus x, then v is minus e minus x. The integration by parts would read off as uv, minus sine x, e minus x between pi and 0, and integrating minus of v times du dx. Because we have minus here, so we can just actually take it as positive, okay. E minus x cos x between pi and 0, dx. Well, you might say that is no good because we still finish with something that's a product of two functions. But does it really? You can see the first part, this bracket goes to 0 because sine pi and sine 0 is 0. So you will read off as pi 0 e minus x cos x dx equivalent to pi 0 e minus x sine x dx. If we integrate by parts for the left hand side again, what we have? Well, let's u to be cos x, du dv to be minus sine x, and dv dx to be e minus x, v is minus e minus x. Now we shall have left hand side to be uv, so minus cos x e minus x between pi and 0. Minus e minus x pi 0 sine x, okay. Equivalent to pi 0 e minus x sine x dx. You can see if we move this part to the right hand side, then we have 2 integration of between pi and 0 e minus x sine x dx equivalent to minus cos x e minus x pi 0. So our integral will be a half of cos x is minus 1, so minus 1 is 1, e minus pi minus plus cos at 0 is 1, so e minus 1. Okay, and that's your solution to part 1. The area A1 is a half of e minus pi plus e minus 1. Interesting. The order of the question is a bit weird, but show that A2 over A1 is e minus pi. Interesting. How should we proceed then? Well, I think we shall write down the explicit integral of A2, which is right. The function keeps the same, it's just bound change between pi to 2 pi. And I think you can see when we're trying to calculate A2, we will follow the same procedure here. So at the end of the day, we shall have this is a half of minus cos x e minus x between pi and 0. Sorry, not pi and 0, 2 pi and 1 pi. That shall gives you a half of minus e minus 2 pi plus is it plus? We got minus a minus 1, so it is indeed a plus. No, it's actually minus. Yeah, it's actually minus, minus, a minus. So it's actually minus here. Minus e minus pi. Okay. And now you can see this integral is negative. Why? Because if you look at the graph, A2 is below the x-axis, so the integral must be negative. So we shall take the absolute value here. And that is equivalent to a half e minus pi plus e minus 1. Wait, I make a mistake here. It's e pi here, actually. Ah, this is where I make a mistake. I was wondering. So that's 1, which is equivalent to 1, actually. So this is actually 1. I make a mistake here. Sorry, chaps, I found I made a mistake here because it should be e to the power of 0. Okay, it should be e to the power of 0 rather than e to the minus 1. That's why I was confused. Apologies. And now we can take a e minus pi out, then we shall have 1 here. So A2 over A1 is a half e minus pi plus 1 over a half e minus pi plus 1. You can see these cancels out, and we're only left behind with e minus pi. Perfect. just as stated. Okay, just as stated. So indeed, a2 over a1 is e minus pi. And for the last part, I think it is given that a minus 1 over a1, sorry, an plus 1 over an is e minus pi. Show that the exact value of the total area enclosed by the curve and x-axis is 1 plus e pi over 2 times e pi minus 1. Perfect. So what we're trying to do is, we're trying to find a1 plus a2 plus a3 plus a4, and goes on and on and on. This is the sum of an infinite sequence. How shall we determine the sum of an infinite sequence? Well, I think the first thing we should do is determine if there's an actual formula for that express an as a formula. Because it says the ratio between the consecutive term is e minus pi, so I think it'll be straightforward to say that an is actually e minus pi to the power of n minus 1 times a1. Right? So that turns our infinite sum to be minus pi n minus 1 a1, or a1 times the infinite sum of n plus n equal to 1 e minus pi n minus 1. And it's a geometric sequence. Geometric sequence. Right. We know the summation is a formula for geometric sequence, especially when e minus pi is less than 1. We know that the infinite sum will converge. Sorry, that is 1 over 1 minus e minus pi. And that is a half e minus pi plus 1 over 1 minus e minus pi. If we multiply by 2, we shall have e minus pi plus 1 over 2 1 minus e minus pi. I think the only thing we can do is multiply by e pi on both top and bottom. And now we shall achieve 1 plus e pi and 2 over e pi minus 1. And that fits the required form. Okay, and that's the end for this question. I think it's a very, very interesting question because if you look at the graph, very complicated. It keeps oscillating until infinity. It's still oscillating. And by our usual formula of integration, we need to take some limits to find the area under the graph. So the area between the graph and x-axis. To show convergence of an infinite or indefinite integral in a sense is quite tricky. You need university level math of analysis to determine if it actually converge. However, if we approach from the other way, the approach is, well, divide the intersection, sorry, the area bounded by the curve and x-axis into such a1, a2, a3, and a4 into an infinite sequence. Okay. And I found out it's actually quite easy to compute the value of the area for each a1, a2, and an. And more importantly, we found out that it's actually a geometric sequence that converges. So convergence of the geometric sequence is well known, and we can use a simple result to prove or to calculate the total area under the graph. If we give it a practical meaning, it might be, well, the total energy in the system and keep oscillating and disperse its energy. Okay, you can see it as the energy, how energy decays as time goes on, whatever. And in the first part, the most tricky one is to find the integral, because e minus x sine x, integrating it, you'll find it's a very, very standard and very interesting integral. It's kind of like oscillating between e minus x sine x and e minus x cos x, when trying to use it differentiate or integrate it by parts. It is this kind of oscillating property to provide us a way to calculate the integral in aim to be integrated twice by parts, and we have the original integral with something else. And now we can equate the integral. If we do further math, you will see these type of integrals more often, but it's kind of rare for just A-level math. Okay, so I think that's one of the benefits of doing practice. Okay, if you practice more, you will see more of these type of questions, and when you see it in exams, you'll not be scared. You'll be confident that you know that you'll be able to deal with these type of integrals. Yeah, I think this is one of the points I missed in the first video, because practice also enhances your confidence. You know that you have encountered so many different questions, and this one is probably just a simple variation from one you have done before. And in this case, you've seen this type of integral now, and next time you meet it, you will not be scared. Okay. And for the second part, obviously, we need to compute A2, right? But we do not compute A2 from first principle again, like we did in part 1. We can use some conclusion, because you can see evaluating the integral does not really kick in at here or here, okay, into here. So basically the bounds we can just carry all the way to the end to let them be unknowns until the very last step, right? So you can just say the integral is just something of this form. We just need to change the bounds here, right? So we can have a simple formula for calculating A2. Obviously, the other thing about A2 is that it's area under the x-axis. So if we calculate the integral just as it is, it'll be negative. And to calculate area, negative is no point. We need to make it positive by taking absolute values. And by taking absolute values, taking ratios, you can see it's actually e minus pi. For the last part, I was quite surprised it didn't actually ask you to prove that e minus pi is a common ratio. You can see if they ask you to prove it, you'll probably use arguments by induction. Okay, you probably use argument by induction, or just calculate by brute force. It's just this formula, okay? Because every an can be calculated by this formula, and I think there's no reason why not you can't prove this statement where the common ratio between the two consecutive area is e minus pi. But anyway, it is given. And for the last part is where we can glue everything together. Okay, we have explicit formula for each of these finite areas. We found that it's a geometric sequence, and if you're trying to find the sum of geometric sequence, we just use a formula where it is 1 over 1 minus the common difference, right? And some changing format in terms of fractions, it'll help you to find the final results. Very interesting problem. You can see geometric sequence, we've done it before. Integration by parts, we could also done it before. And it's only the integral, the tricky integral, we have never encountered before. But if you observe it carefully, you still would have a clue, right? And the most important thing I want to take away from this question is those seemingly difficult questions based on materials and information or knowledge we have encountered before. You must stay patient, analyze the questions, think about what's asking you and why they split the question to this way. And many times, they will give you an approach of telling you how to solve this question, including this one. So I hope you learned something useful from this video, and see you next time. Bye bye.